Okay, my dear students, now we are going to discuss on isometric projections in module 10. So we have been seeing till the 9th module, all these are orthographic projections. Now we are going to see a different projection, that is called isometric projection. So the importance of this isometric projection, you can see this is the Taj Mahal, isometric projection of the Taj Mahal. So here you see all the 3 dimensions of the object, unlike in the orthographic projections. If you take the top view, you don't see the height. If you see the front view, you don't see the breadth. So or length. So you will be missing one of the 3 dimensions in the orthographic projections. But in the isometric projections, you can see all the 3 dimensions in a single projection. That is, they are easy to understand also. For any layman, one can understand the object easily by looking at the isometric projection rather than from the orthographic projection. For example, another example, you see this is how in a room with the furniture, sofa, all these things are arranged. So you will see all the 3 dimensions of every object. So it gives a better idea how the inside room is, rather than giving simply the front view or top view. Again, this is also an isometric view of a house. So you see here not all the 3 dimensions. See the breadth, this is the length of the house, and height, all the 3 dimensions in a single projection. So this gives a better idea for an educated person or an uneducated person, an engineer or a non-engineer. So again, this is another picture with all the inner details in a house or office. So now look at this object, simple object, cube. On the left side, you see the orthographic projections. So it is very difficult to imagine how the actual shape of the solid. But if you look at the right side, isometric projection, it is easy for anybody, whether it is for an engineering student or a non-engineering student, how the object is. So one can easily understand from the isometric projection rather than from the orthographic projection. So this is an example of the advantage of isometric projection. Again, you look at, see the cube, this is the isometric projection of the cube. You can see the top, left side, right side, all are visible in the single projection, that is isometric projection. But their actual shapes are square. You look at this, actual shape is a square, whether it is right side or left side or top, but they look like rhombus. They look like rhombus. This is one thing you can observe. Another thing, the axis, x-axis, y-axis, z-axis, they are actually at 90 degrees. The angle between the axis is actually 90, but here you see them as 120 degrees. The angle between xy or x and z or y and z, the angle is 120 degrees. So these are called isometric axes. Now the principles involved in drawing the isometric projections are derived from the cube. This problem we have discussed in the projections of solids, where a cube is resting on HP and with the faces equally inclined. Now the solid diagonal we have considered 1 dash 3 dash, and this is parallel to HP and perpendicular to VP. So for this particular position of the cube, the final front view is this, which is looking like a regular hexagon. So this is nothing but the isometric projection of the cube. So that means we cannot draw all these steps for every object to get the isometric projection. So one thing we should understand here, this is the solid diagonals. So if you can see along the solid diagonal, and if you have project it on a plane perpendicular to the solid diagonal, you will get directly the isometric projection. So the angle at which we have to see is nothing but the angle made by the solid diagonal. So we are seeing the object at an angle to get the isometric projection, unlike in the orthographic projections where we see from the front and we see from the top. Here we see at an angle to the horizontal plane, that is the angle made by the solid diagonal. What is that angle? Also you can see from this. Same thing, the projections are shown by using auxiliary plane method, and if you can also mathematically find out what is that angle. If you take the height of the cube as a and side of the cube also as small a, and the angle you get is tan theta is 1 by root 2 or theta is 35 degrees 16 seconds. So this is the angle at which you have to see any object to get the isometric projection. So how to see at that particular angle is very difficult. Therefore, by looking at this particular angle, the dimensions get reduced. So here if you see, the actual height of the cube is a, but what you see in the isometric projection is a cos theta. So it gets reduced by how much? You can see here it is indicated. It is what is a cos 35 degrees 16 seconds? It is a times 0.816. So nearly 20% of length gets reduced. You will see only 80% length. So there will be reduction in the dimensions by 20% nearly in the isometric projection. All dimensions all get reduced to 20%. So now you look at this. These are the OX, OY, OZ. They are the isometric axis. Generally X and Y are taken as inclined at 30 degrees to the horizontal line, and the vertical line always represents the Z axis to represent the heights. So if you look at this figure, A figure indicates the isometric axis, that is X and Y. They are generally inclined at 30 degrees to the horizontal. Z axis is usually perpendicular to that, which is used for representing the heights. And the B figure indicates the cube in the isometric projection. You can see the edges are parallel to X, Y and Z. Now the top one, if you take top A, C, B, D, which is actually a square, but it looks like a rhombus. So here in the figure C, both the views are drawn, actual shape and the shape in the isometric projection. So from this we can derive the isometric scale. So AP, the line AP, that is the side of the cube, actually that is AP, but AD is the representation of AP in the isometric projection. So the length of AD is lesser than the length AP. AP is having true length, but AP in the isometric, AD in the isometric projection, it gets reduced. So how? Instead of using the calculator or any mathematical tool, one can easily convert the dimensions from actual dimensions to isometric by using this, what is called an isometric scale. So you can see this here, black line is a line on which you get the isometric lengths. The red line is the line on which you will have true lengths. So first you draw one horizontal, that is the blue line, then you draw two lines, black and red, at 30 degrees and 45 degrees. Okay, so AB, AB1 and AB. On AB1, you mark the actual dimensions, say 10 mm, 20 mm, 30 mm, 40 mm, like that. So the corresponding lengths in the isometric you will get by just dropping a normals from the red points on the red line onto the dark line or black line. You measure from A on the black line, that is isometric lengths you will get corresponding to 10, 20, 30, 40. So the equivalent of 10, 20, 30, 40 true lengths you will get on the isometric length. Okay, this is how first before you start doing any isometric projection, to convert the dimensions you should construct the scale on one corner of the drawing sheet. See, you see here a cube drawn without converting the dimensions with converting the dimensions. The projection, isometric drawn without converting the dimensions is called as isometric view. Please remember the difference. Isometric view means without converting the dimensions, drawing the isometric, whereas isometric projection means converting the dimensions and then drawing the isometric. So that is called a projection, and this is called, the first one without conversion is called a view. So if you look at these two, the view will be naturally bigger than the projection, because in the projection the lengths get reduced by nearly 20%. So the size will be different, but actual shape of the views will be same. Isometric will be same, but only size will be varying. Now to apply this, of course we have to start with the plane figures. Then that is two-dimensional objects first, then you will take up three-dimensional objects. So we can take up a triangle. See here a triangle is taken of say 40 mm base and height to 20 mm. Say this is how 1, 2, 3 is the triangle, actual triangle, which we have to draw the isometric projection. So if you want to draw projection means you convert the dimensions and then you have to draw. So again, which plane you have to use, because this is a plane figure, it's a two-dimensional one, you can draw either in the XY plane or YZ plane or in the XZ plane. Usually, unless otherwise mentioned, you draw in the XY plane. So you draw X and Y inclined at 30 degrees to horizontal line, then you mark a 2, 3 on that. So first concept here is, any figure you enclose it in a rectangle. So this triangle is enclosed in a rectangle of ABCD. See, BC is same as 2, 3, and but point 1 lies on AD. So first you take ABCD as the rectangle and you put one side of the rectangle on x-axis, another side on the y-axis. Say BC is on x-axis and BA is on y-axis. So you mark the corresponding lengths and draw the rectangle. But the given problem is not rectangle, it is a triangle. So the point 1 lies on AD. So you take the distance of 1 from A or from D, you mark on this, and simply you join that point 1, 2, 2 and 3. So 1, 2, 3 here now represents the isometric projection of the triangle in the XY plane. Similarly, you can show, you can draw in the YZ plane in the same manner, first drawing the rectangle and then finding the points 1, 2, 3. Similarly in the XZ plane. So unless otherwise mentioned, usually plane figures are represented in the XY plane. So another example is taken, a pentagon. Again, to draw the pentagon, one side will be given. So first construct the pentagon. Say 25 mm is the side. If you want to draw the projection, first you find the conversion, convert 25 into isometric length, you take that one as 1, 2 and construct the pentagon and enclose that pentagon in a rectangle, that is ABCD. So their first square or rectangle So you enclose that, you will get the dimensions of the rectangle ABCD, and after getting the dimensions you take in the XY plane, first you draw ABCD, and on the corresponding sides, say on AB 5.5, on BC 1 and 2, on CD 3 and DA 4, you mark the same distances from this figure and mark on the corresponding. You will get join all 1, 2, 3, 4, 5, you will get pentagon in the XY plane, isometric projection of a pentagon in the XY plane. Similarly in the YZ or XZ. So the principle here is, first you draw converting the dimension, the pentagon. So first, any plane figure, you first draw converting the given dimensions into isometric lengths. Then enclose that in a smallest rectangle possible, and then draw that rectangle in the XY plane or YZ or XZ plane, and then later on the corresponding points you can locate on the four sides of the rectangle and join them by straight lines. So this is a circle. Circle again, the given diameter you convert into isometric length, and using that as diameter you draw the circle. Now after drawing the circle, you enclose that circle in a rectangle square ABCD. So the midpoints of the sides will be on the circle, say that is 1, 3, 5, 7. But another 4 more points you need. So you join the diagonals, that is AC, BD, which will cut the circle at 2, 4, 6, 8. So now you join them, you get another square. So here you have two squares, ABCD one, another 2, 4, 6, 8. So one inside the other. So just like in the previous cases, you take XY plane. First you draw one square on the XY plane ABCD, and then draw the another smaller square inside by adopting how much you have to reduce from the bigger one. So draw just 4 lines inside, parallel lines, and then you will get 2, 4, 6, 8. So the midpoints of the outer, that is rhombus, bigger rhombus, and the corners of the smaller rhombus you join by a smooth curve, you will get 1, 2, 3, 4, 5, 6, which will circle looks like an ellipse in the isometric projection. So again YZ in the XZ plane. So it same, it looks like an ellipse, only thing is it will be in the XY plane, YZ and XZ plane. So the way, another method, there is another method by which you can draw the ellipse, that is isometric projection of the circle in the can be drawn in a different way, provided the ellipse is sufficiently big to draw arcs. This is called 4 arcs method. This is called 4 arcs method. So what is this method? Sometimes this gives a better isometric projection. Instead of drawing with freehand, you can draw with using the compass. So here first you draw ABCD, that is the outer rhombus. Then what you do is take the midpoints of the 4 sides. See, you join D to G, you will get the point of intersection with the AC. Similarly, you draw B to E, it will also cut at another point. You take these points, you take as these are centers, you draw 2 arcs, one on the other one side. Here this one as center, you draw another arc. So 2 arcs with radius equal to this one, small one. Then you take B and D as radius centers, with BE or DG as radius, you draw 2 big arcs. So 2 big arcs, 2 small arcs, total with 4 arcs, you will get the total shape of the ellipse. So this is called a 4 arcs method. This can be adopted provided the size of the circle is sufficiently big. Now coming to solids, first let us see, we are taking some different problems, say pentagonal prism, pentagonal pyramid, cylinder and cone. So we are taking 4 different types of solids, a prism, pyramid, a cylinder and a cone. So here you see this is a prism, a pentagonal prism. So how many dimensions you will have? Side of the base and height. So both these dimensions you have to first convert. This is how you draw the isometric scale, and those 2 dimensions you will convert. After converting, you draw this first pentagon using the converted dimension, enclose it in a square, and now you draw first in the xy plane the square, and in the z plane you take the height. So you will first draw it as a square prism or rectangular prism. Then you mark the 5 points on the top and bottom, and you will join vertical lines and base edges. You will get the isometric projection of the prism. This with the axis along z axis, axis along z axis. Same thing, we can take axis along x axis or axis along y axis. The procedure is same. Here this is a pyramid. Same, only difference between the prism and the pyramid is there will be only one base. Whereas pyramid you will have apex on the other side. Instead of second base, you will have apex. So first you draw the bottom base, then take the center of the bottom base and you erect a perpendicular. On this perpendicular you put the height of the pyramid and you will get the apex. And after getting the apex, you join to 5 different points of the base. They are slant edges. So you will get the isometric projection of the pyramid with axis parallel to z axis. Similarly, axis along x axis, axis along y axis also you can draw. So the base first is taken along xy. Here base is taken in the yz. Here base is taken in the xz plane. Automatically the axis will be in the along the third. So here is cylinder and cone. Again in the all the here also first the axis is taken in the xy plane. I mean z axis, base in the xy plane. So first you draw the bottom base and get all the 8 points on the bottom base. From all the 8 points on the base, you erect perpendiculars, you mark height on the, you will get the top ellipse. Or another way, you draw both bottom rhombus and top rhombus, you mark, get the 8 points and join 1 to 1. So you will get the cylinder. So here in this case axis is parallel to x axis, here axis is parallel to y axis, cylinder. Same in the same manner here for a cone, first you draw the base, afterwards take the center, you draw vertical line, you will get the apex. After getting the apex, you join to 8 points of the base circle, they are generators. So this is axis parallel to z axis. Here axis parallel to x axis, axis parallel to y axis. So say a particular problem is taken here, a pyramid, I mean pentagonal pyramid. See, for that you are given 2 dimensions, side of the base is 30, height is 70. See what is that isometric projection. Please read the problem, whether projection is asked or view is asked. If projection is asked, dimensions should be converted. If view is asked, you can adopt the same dimensions. So first construct the pentagon, because projection is given, you convert 30 and then draw the pentagon. You will get the rectangle ABCD. You draw the rectangle in the isometric, mark the 5 points and then take the center, you erect perpendicular, and then mark converted 70 mm to get the apex. You join all the 5 points. So that is how you have to do for a pentagonal pyramid. So various steps are given. This is a frustum of the cone. Here also, the only difference between this and the cylinder is both the top and bottom will have same diameters, but here they are unequal. So same procedure you can adopt. First you draw the base bottom, where you will get a bigger ellipse. Same thing you adopt at the given height, you will get a smaller ellipse, and you join the tangents to both the ellipse. You will get the isometric projection of the frustum of the cone. So this is again another pyramid problem, and you have to draw, if necessary, both the top view and front view sometimes. In this problem, you have to draw both the top view and front view. Sometimes it is enough only if you draw the top view, but here in this case, you have to know the heights of the various points, that is A dash, B dash, C dash, E, F dash. So these heights only you get in the front view, so that you can adopt in the isometric projection. So all the points are having different heights. So in this case you have to draw both orthographic projections, top and front views. So first you will draw the base, and on that you will get the 6 points of the hexagon, and then you will draw the section a small a, b, c, d, e, f by taking their coordinates, and from those points you erect perpendiculars, mark the heights of each point. You will get the capital letters A, B, C, D, E, F. You join them as shown. That will give the isometric projection of a sectioned solid. This is a isometric projection of a sectioned object, that is a pyramid. Now coming to isometric projection of a sphere and spheres on a cube. So sometimes only sphere or a sphere resting on some other solids will be given. Let us see first the property of the sphere. We have discussed it in the projections of solids, the sphere. This is the front view of the sphere, this is the top view. How do you identify the front view and top view? Front view, we will have center C dash at the center, the point of contact P dash on the circle touching the XY line. If you look at the top view, both C and P, center and point of contact, both will be at the center of the circle. So by this you will be knowing which is the top view, which is the front view, because both are circles, but how you name them, where are the points, center and point of contact, that makes the difference. Even in the isometric projection, it looks like a circle, but where will be the point C, where will be the point P? C will be at the center, but P will be neither on the circle nor at the center. It will be inside the circle. The point of contact of the sphere will be inside the circle. By how much distance? It is by true radius minus isometric radius. So it will be inside by the difference between the two radii, or it will be at an isometric radius from the center C. So you take center C, you drop a vertical and mark point P at isometric radius, so which will come inside the circle. So this is the point of contact with the ground or any other object on which it is resting. So keeping in mind these, how you will be able to identify which is the projection, isometric or orthographic. Now in this figure, sphere is resting on a cube. So first you will draw cube, and then on the top of the cube you find the center point, that will be P. So that is where it should touch, sphere should touch. From knowing the point P, you erect a perpendicular, mark isometric length, you will get C, and then you draw a circle with the true radius and then you will get the point P inside the circle. So this is how you can consider sphere on any solid. Please remember one thing, there is no isometric view for sphere. Only whenever sphere is there, you have to give isometric projection, because the point P we must inside. So if you don't adopt isometric projection, if you draw isometric view, P will come on the circle. If it comes on the circle, it indicates as a front view. So please remember, this is a very important point. Wherever sphere comes, sphere resting on some other solids, you have to adopt isometric projection, though you are asked to give isometric view. So these are the various points we explained. So this very important note you have to keep in mind. When the isometric projection of the sphere or hemisphere or part of the sphere are to be drawn, then only isometric dimension should be used. There is no isometric view for sphere or sphere with other solids. Only projection has to be drawn. So you can try. See, examples are given for a rectangular block. 3 views of the orthographic projections are given and its isometric is given. So you can observe which is easy to understand. This is another example as explained earlier. Orthographic projection is given and its corresponding isometric. So these are the steps. So it's one you can observe. The 3 views of the steps in the orthographic projection are given and its isometric projection is indicated. This is another V block. So you will be given orthographic projections, so you have to draw isometric projection. So you can try from these exercise. Various plane figures are given and solids are given, and these are multi-solids, problems on multi-solids, say one over the other, a truncated pyramid or prism with a frustum of the cone and a sphere resting. So these are called multi-solid problems. This is another some castings. So you will be given orthographic projections like this. You have to imagine and draw the isometric projection. Okay, thank you.